Hey guys, Mr. L coming back at you with another video. And in this video, we're going to continue our atomic trend section. So if you haven't watched the first video, make sure you go back and watch that to understand effective nuclear charge. And in this video, we're going to talk about ionization energy, electron configurations of ions, whether they've gained or lost electron affinity, as well as a lot of different group trends that we have for the alkali metals, alkaline earth metals, halogens, and noble gases. So let's get into this video. So the first thing we're going to talk about in this video is ionization energy. So let's define ionization energy. Ionization energy is the minimum amount of energy it's required to remove an electron from a neutral gaseous atom. So we have to make sure that the atoms in the gas phase, we're going to put in energy, and that energy is going to knock off the easiest to remove valence electron. So we have to do this in subsequent order. We're going to put in energy to a neutral atom, and that output of this is going to be a positively charged ion in the gas phase plus the electron that we removed. So the first ionization energy is going to be the energy required to remove the first valence electron. And then all of these removals have to be subsequent. So you have to remove one electron before you can remove the next, before you can remove the next. So the second ionization energy is going to be the output of the first. So you're going to start with a positively charged ion. You're going to put in energy and you're going to remove a second ion. So your product should be a doubly +2 charged ion in the gas phase. So the removal of one electron is going to be the easiest electron to remove, and each time you go to remove a second electron, it's going to take more and more energy. And that's because you have the same number of protons in the nucleus, and each time you remove an electron, you've got more and more pulling power on the remaining electrons. So the first one's always easy to remove compared to the rest, and then it gets harder and harder with each electron that you remove. After you remove all of the valence electrons, you're going to be left with core electrons, and you're going to basically hit an energy barrier where it's going to take an extreme amount of energy compared to the valence electrons to start to remove core electrons. So now that we have an understanding of ionization energy and removing electrons, let's talk about electron configurations of ions. It's going to be the exact same way that we do electron configurations for neutral atoms, starting with the 1s and going with the 2s. But you're just going to remove or add electrons depending on whether it's positive or negative charge. So if we have something like lithium ions +1 charge, neutral lithium's configuration normally has 3 electrons, 1s2, 2s1. So lithium +1 ions electron configuration is going to be removing 1 electron, and that's going to come from its valence shell. So the 2s electron is going to be removed, and lithium's ion electron configuration should be the same as helium, and it's just 1s2. So if we're thinking about our trend for ionization energy is going to increase across a period. So the reason why it increases across a period, if we go back to our first trend that dictates all the rest, the effective nuclear charge is increasing across the period. So if the positive charge in the nucleus is getting higher and higher and higher by the addition of more and more protons, then your pull is going to be stronger and stronger on each of those electrons. Therefore, it's going to take more energy to remove a valence electron if we have higher effective nuclear charge. So across a period from left to right, ionization energy is going to increase. If we're thinking about within a group, as we go down a group, we have more and more core electrons, which acts as a shielding or a screening constant. So we have more and more shielding, and the valence electrons further and further away from the nucleus, it's going to be easier to remove the valence electron as we go down a group. So top right is the highest ionization energy, and bottom left should be the lowest ionization energy. The next trend that we're going to talk about is electron affinity. So if we think about the word affinity, it means affection. So if your grandma has affection for you, she likes you and she wants to have you around and bake you cookies. Well, some atoms really love electrons. They have high affinity for electrons. So electron affinity is defined as the energy change that's accompanied by the addition of an electron. So you're going to have a neutral gaseous atom in the gas phase, and we're going to give it electrons, and we're going to measure to see how much energy is released. So this energy value is going to be a negative value because when the electron is gained by this atom, it's going to dissipate the energy out because it's in a happier state. So if we're thinking about an equation for this, it's going to be a little different than ionization energy. We're going to have neutral gaseous atom plus a free electron, and that's going to yield us a negatively charged ion in the gas phase plus that energy that's been released. So if we're thinking about our trend electron affinity in terms of location on the periodic table, within a period, it generally increases as we go across a period because we're getting closer and closer to noble gas configuration. So something like a halogen, like chlorine or fluorine, they would love to gain one remaining electron to complete a noble gas configuration, and they're going to dissipate a lot of energy by doing this. Not much changes within a group though, because it's based on the same electron configuration. All of the halogens are going to end with S2P5, so all of them have one remaining slot for that extra electron to fit into, so that we don't really have that much changing within a group in terms of electron affinity. So in a previous video, we discussed the difference between metals and nonmetals, and we can start to continue this list that we've compiled of properties of metals versus nonmetals. So if we just remember, metals are typically on the left and the middle side of the periodic table, besides hydrogen, so keep in mind hydrogen, and a lot of these metals tend to lose electrons or form cations. So now we can understand why these form cations. It's because they have lower effective nuclear charge compared to nonmetals further to the right within the period. Because the effective nuclear charge is lower, it's much easier for them to lose their electrons or have the electrons stripped from them. They have very low ionization energy, so it doesn't take a lot of energy to do this. And a lot of the compounds that are formed between metals and something else are going to be ionic in character. So if we're talking about nonmetals, those are again on the upper right side with the exception of hydrogen, and they tend to form anions. And the reason for this is because they have high electron affinity. They love electrons. So when they gain electron, it's going to dissipate energy, and they're going to be happier in this electron configuration by gaining electrons. They have high ionization energy because they have high effective nuclear charge, so it's much harder to rip electrons from a nonmetal. And when these nonmetals tend to form compounds, they tend to form molecular compounds. So some new things that we're going to add to the list besides this new ionization energy and electron affinity is the idea of when we have a metal oxide. If you have a metal that's been ionically bonded to an oxide ion, so something like sodium oxide, if we were to add sodium oxide to water, this is going to cause us to have a basic solution. So that means the pH is going to be greater than 7. The opposite is going to be true of nonmetal oxides. If we have something like carbon dioxide, a nonmetal oxide, and we were to add that to water, we're going to produce carbonic acid. And that's going to lower the pH, so the pH value is going to be less than 7. So metal oxides form basic solutions, and nonmetal oxides form acidic solutions. And then we have the metalloids, which were on the staircase area of the periodic table. And these again have properties of both metals and nonmetals. And we use these a lot in computer systems because they are semiconductors. So now what we're going to do is we're going to discuss some group properties. So the groups that we're going to focus on are alkaline metals, alkaline earth metals, chalcogens are the one with oxygen at the top of the group, halogens, and noble gases. So let's talk about alkali metals first. Alkali metals are very soft. You can cut a lot of the alkali metals, even though they're metals, with a butter knife. They're very soft. And when you go to purchase them, they're going to come in a jar submerged in mineral oil. So the metal is going to be submerged in mineral oil. And the reason for this is they're very reactive. They have one valence electron, and we saw that that one valence electron is going to have a very low energy value for that electron to be removed. So these are very reactive, and we don't find pure alkali metals out in nature. We always find them bonded with something else because it's very easy for something else to go rip that electron and form a cation and for those opposite charges to stick together. They have very typical metallic properties such as they're conductive, they're very shiny and lustrous, they have very low density, and they have very low melting points, so they melt very easily. These are very, very exothermic. What that means is it's going to release a lot of energy by reacting with something. So if you were to take a pure alkali metal and even throw it into water, the alkali metal will actually catch on fire in water, and a lot of them will even explode because such a great amount of energy will be released by these alkali metals. So they're extremely reactive. When the alkali metal reacts with oxygen, it can form oxides, so something like sodium oxide, Na2O. A peroxide is an O2 minus 2 ion, so each oxygen would have a formal charge of a -1 on it, as well as superoxides. We're not going to focus too much on superoxides, but I just want you to know that they exist. The other really cool thing that you could do with alkali metals and a lot of other metals is we can do flame tests to them, and we can see their valence electrons get excited and fall back down to the ground state, and they're going to emit photons in the visible region. So let's look at some flame tests to see what different colors that we can get. All right, so here we are in the bench top, and what we're going to do is we're going to excite electrons of different metals to cause them to get excited, fall back down to the ground state, and depending on their unique electron configurations, they're going to emit photons within the visible region. So let's take a look at this metal. So let's put in energy and then excite the electrons and see what color in the visible region that we can get. So here we're giving off a nice green color. So this is a nice green emission, and this is coming from copper. So copper emits in the green visible region. The next one we got here is calcium. So let's see what color calcium excites to. So there we go. Calcium emits in the orange visible region. So samples with calcium are going to have orange emissions. Next we have sodium. We could see sodium emits in the yellow region. So a lot of the street lamps that we have next to sidewalks, this is why they have a yellow glow, is sodium emits in the yellow region. And the last one we have here is potassium. So let's see what color potassium emits in. So that's a nice light purple color. So potassium emits in the purple region. So we can see that depending on the different metal that we have, we can excite those electrons, and we can start to qualitatively identify what metals might be in a sample based on its flame emission. So the next group we're going to talk about are the alkaline earth metals. The alkaline earth metals are very metallic, just like alkali metals. They're very silvery. They're a bit harder. They have higher density and higher melting points than alkaline metals. You can also excite them, just like we did for calcium, if we're going to do a flame test. And some of these are reactive, but they're not nearly as reactive as alkali metals. They're not going to explode in water or catch fire in water. Beryllium does not react at all with water, and magnesium only reacts with steam. So you're going to need to put a lot of energy into water to cause it to go into the steam or the gas phase to be able to interact with magnesium. But then everything below magnesium, so like calcium and strontium, if you drop those pure metals into water, they're going to begin to release electrons because they have more shielding than beryllium or magnesium. So they're going to give off electrons into water, and you're going to see a lot of bubble gas forming, and that's going to be hydrogen gas. So reactivity is going to go down the group. It's going to increase in reactivity down the group. The next group we're going to talk a little bit about are the chalcogens, or the ones with oxygen at the top of the group. This one we're going to focus on a little bit because it's so unique. You've got oxygen, which is very non-metal, has high electron affinity, As you go down the group, you go to a solid sulfur, and those are gonna love electrons as well. It's gonna have high electron affinity. But then as we start to go down and down the group further, the properties become more and more metallic, and by the time you get to the bottom of the group, you have polonium, which is a radioactive metal. So you could see the properties are going to vary greatly within the chalcogens, and this just shows you the continuum of different properties that you could have even within one group. The next group we have are the halogens, and the halogens are very, very typical nonmetals. They love to rip electrons from other things, so they have very high electron affinity. They love electrons. So they tend to exist as ions in the negative charge. Anions. They tend to exist as anions. And they bond directly with metals to form ionic compounds, metal halides. All of these are going to end with S2P5 for their electron configuration, so they're one away from an octet or a noble gas configuration. They have very low density for the most part, which is why they're existing in gas. Gas has very low density compared to solid or liquid. We have the one liquid bromine within the halogens, as well as these have very high ionization energies. It requires a lot of energy to remove an electron from a halogen. And the last group is the noble gases. They have a full S and P shell, so they have a full octet, so they end with S2P6, and this is why they don't exist as compounds. We find noble gases as monoatomic, meaning single atoms floating around, and that's because they don't have any available slots for bonding. So typically you're not going to form compounds with noble gases. The only ones that can possibly form a compound are the larger noble gases that have a lot of shielding, and an element only like fluorine will be able to rip electrons from a noble gas. But again, this is going to be in a rare lab circumstance. For your purposes, noble gases don't really bond with anything. So there it is, you guys. There's part 2 of atomic trends, ionization energy, electron affinity, ion-electron configurations, and some group properties. So if you enjoyed this video, if you found it useful, smash the like button, subscribe, send it to your favorite porcupine, send it to your favorite giraffe, and we'll see you in the next video.